Hi, and welcome to this lesson on solving two-step inequalities. This is Concept 15 in Unit 2. Please make sure that you are taking notes in the packet. You can pause and rewind when you need to, and write down any questions you might have. So an important thing to know is that solving inequalities is just like solving equations, with one special rule. We're going to get to that special rule in a little bit. First, we're going to see how this is just like solving equations. Remember, equations are things that have an equal sign. Inequalities, there are 4 different inequalities. There's less than, is greater than, is less than or equal to, and is greater than or equal to. So in this inequality, we're using is greater than, and we're asked to solve, which means the same thing as it did when we were getting equations to solve, which is get the variable alone. In this case, the variable is x, so our goal is to get x alone. Right now, on that side of the inequality, there's a 5, a constant in the way of x being alone. And so in order to get that constant removed, we're going to use its additive inverse. And like always, we do the same thing to both sides. This means that 5 is eliminated from the left side. We have x, we bring down the inequality, don't make a typo and accidentally put an equal sign. And we have 20 minus 5, which is 15. And so we have just solved our inequality. If we wanted to graph this inequality, we'd put our critical number, 15, in the middle of our number line, and then just one number to the left and one number to the right to give some scale to our number line. Then notice that this inequality is greater than is one of those not included symbols, so we use an open circle. And then we're going to ask, which way do we shade? We always shade in the true direction. Since 16 is greater than 15, that is true, we're going to shade to right. I'm going to make my arrow look a little neater. Maybe I'll just end it there. Okay. Remember, open circle, shading in the true direction. Then we're asked some follow-up questions here, and this is a little new. It says, is 10 in the solution set? So that we know, the solution set includes all of the numbers that make the inequality true. Make sure that you have that in your notes. The solution set is all of the numbers that make the inequality true. So we're going to ask ourselves, is 10 greater than 15? And since 10 is not greater than 15, no, 10 is not in the solution set. You can also think about where 10 would be on this number line, which is way down here. And notice that this side is not shaded, so therefore it's not in the solution set. The next question asks, is 1,000 in the solution set? 1,000 is in the solution set because if we substitute it into the inequality, right, which said x is greater than 15, we can see that 1,000 is greater than 15. That's a check mark, so yes, it is in the solution set. If we used that same strategy up here, we would have had 10 is greater than 15, and that is not true, so this was a no. Next we're asked, is 15 in the solution set? Remember, again, our inequality is x is greater than 15, so we're asking ourselves, is 15 greater than 15? And no, 15 is not greater than 15 because they are equal, so no, 15 is not in the solution set. Now, this one, where the numbers are the same on both sides of the inequality, is sometimes tricky. We have to be careful that we know what each inequality symbol means, and the Regents knows this and likes to ask that question, so please be careful. Let's take a look at another inequality. Again, we are asked to solve, which means we want to get the variable alone, but in this case, what's in the way of the variable being alone is a coefficient. Again, solving inequalities is just like solving equations with one special rule that we haven't gotten to yet. So just like we would when we're solving an equation, we divide both sides by the coefficient, and we're left with x on the left side is greater than negative 30 divided by 10 is negative 3. So our answer is x is greater than negative 3. I'm going to clear my workspace a little. Okay, and I'm just going to try to move this ink around a little bit, but there we go. We'll do that. There's our solution. You can rewind if you need to see again how it was done. To graph this inequality, again, I put the critical number, in this case negative 3, on the number line and a number to the left and the right. Now, this is the negative side of the number line, so notice there's negative 2 to the right and negative 4 to the left. This inequality symbol is greater than. It tells us to use an open circle because it's not included. And we have to shade in the true direction. This said x is greater than negative 3. So we're going to shade to the right because negative 2 is greater than negative 3. There we go. Again, they're asking us some questions about the solution set. Remember, when we hear solution set, we should think, okay, this is something that is true. We box that action word and we can expand on it. Solutions, true. So is 10 in the solution set? Is 10 greater than negative 3? Yes, 10 is greater than negative 3, therefore 10 is in the solution set. B says, is negative 3 in the solution set? So is negative 3 greater than negative 3? No. Since negative 3 and negative 3 are equal, and this is a not included symbol, we have not a true statement here, right? Negative 3 is not greater than negative 3, so negative 3 is not in the solution set. Finally, they say, is 3 in the solution set? What inequality would you set up to solve or ask question for yourself? The inequality that we set up would be replacing the variable with the number they gave, which is 3, greater than negative 3, and then asking, is 3 greater than negative 3? And the answer to that question is yes. So this is in the solution set. You can also think about where 3 would be down the number line here, and that might also help you visualize your answer. So far we've said that solving inequalities is just like solving equations with one special rule. So far, none of these inequalities have had us use that special rule, but we're going to do a little discovery now to see if we can figure out that rule on our own. So pause here and write an inequality to make each statement true. For example, and actually we're going to do this a little bit. We know that there are 4 inequality symbols, but we'd like you to use only, for this example, you should only use is less than and is greater than. So inequalities are less than, greater than, less than or equal to, greater than or equal to, but for this we'd like you to just use these 2 symbols. So in example A, 7 and 9, we should put is less than because 7 is less than 9. Take a moment and try the rest of these A, B, C, D, E, F on your own. The inequality symbols that you should have now been almost filled in. E is a little bit tricky. You have to think about those negatives, but negative 4 is greater than negative 5 because it's better to be short negative $4, for example, than short negative $5. Now that you've answered those questions, it's on the next page. This is where we're trying to look for patterns. It says, how are the inequalities in A and B similar? So we're looking at these 2 inequalities. Pause and write down what you notice about how they are similar. And how are they different? Think about what one operation, so operations, addition, subtraction, multiplication. Sorry about that page flip, I'm right by the bottom of my page. Operations, addition, subtraction, multiplication, division could we do to 7 and 9 to get negative 7 and negative 9. So some things that you may have noticed that they're similar because they both have the numbers 7 and 9, but they're because in B, both 7 and 9 were negative. Another way that they're different is that the inequalities are now flipping direction, right? So 7 and 9 were both the same, but they're different in that they have those negatives and then the inequalities flipped. One operation we could do is multiply by negative 1. If we multiply by negative 1 on both sides here, that would give us negative 9, and that would give us negative 7. We did the same thing, one operation to both sides, to get negative 7 and negative 9. Let's do a similar activity for the examples in C, D, and EF. Think about it. What one operation could we do to 10 and 5, negative 2 and negative 1? And what one operation could we do to negative 4 and negative 5 to get 8 and 10? In C, you might have noticed that both of these numbers got smaller, and what we could have done is divide, not by negative 2, sorry, that looked like a 2. If we divide both sides by negative 5, we would have gotten negative 2 and negative 1. You might have also written that you multiplied by a negative 1/2, which is valid. In E and F, what we could have done is multiplied by negative 2 on both sides to get negative 4 to become positive 8, and negative 5 to become positive 10, and negative 2. You may have also noticed that in each of these, A and B, C and D, E and F, something happened to the inequality sign. Notice that is greater than became is less than, and is greater than became is less than here. In the first example, is less than became is greater than. So in each example, these inequalities, we say, flipped. They changed direction. A special rule that applies to all inequalities, which says that if we divide or multiply by a negative, we flip the inequality. These examples are what prove that that's true, and you can try this with any numbers. However, when we're solving with inequalities that have variables, we have to know this rule because it won't be as clear since we're working with unknown numbers, which are represented by variables. So for example, when we're solving example 3, to get this variable x alone, we have to divide by negative 2. We do that to both sides, just like normal with equations, but there's this special rule, and we have to recognize it when it happens. Since we're dividing by negative 2, we realize that we're dividing by a negative, so this inequality is going to flip. It was is greater than or equal to, and our new answer will be is less than or equal to. Like normal, this coefficient is canceled out when we divide by it, and we're left with just x. And like normal, 18 divided by negative 2 is negative 9. And this is our final answer. So it's really important that you have that correct inequality symbol, otherwise this answer would be wrong. Example 4 has a constant, which we must eliminate first, and we do the same thing to both sides. And we have 16 minus 4, which is 12. And so far, we are okay. Notice I brought the inequality sign down just the way it was because we did not use the special rule. We were not dividing or multiplying by a negative. But now, I notice our coefficient is negative 6, and we're going to have to divide by negative 6 on both sides, which eliminates the coefficient. And we can bring everything else down like normal, but be careful. Sometimes people forget this, and this is what makes their answer wrong, so we want to be very, very careful if we divide or multiply by a negative, and we don't forget to flip that inequality. So the correct answer to this is x is less than negative 2. So for homework tonight, please try 2 more examples, example 5 and example 6. Be sure to think back to some other skills you've learned to remember what is considered part of the solution set when you answer example 5. And think about in example 6, where you have everything being divided by 3, what would be the inverse of dividing by 3? As a way to get started, that inverse is multiplication, and what you do to one side, you do to the other. This will give you a much simpler equation to continue with, but you should try that on your own and be ready to ask questions and maybe even present tomorrow in class.